Let's get started, lecture 21. Again, you have to remember what we just reviewed in lecture 20. And also, I strongly recommend you to read lecture note 14, okay, before you further go to lecture 21. And lecture note 14 is about the first law of thermodynamics for the steady flow devices. And we are going to talk about in lecture 21 turbines and compressors, pumps, and even nozzles. Okay. I really want you to remember that the work is for the actual process is different from the reversible process or ideal process. Okay. When your system does a work, produces a work, then the actual work is always smaller than the reversible work. When your device needs certain work input, then the actual work that you need is always greater than the work you need for the reversible case. Okay? Then that's what you're gonna use. Because the real case, the work is different from the ideal case, then we need a very convenient tool to compare this actual case and the ideal case. Now, that is the isentropic efficiency. So basically, the objective of isentropic efficiency is to compare the actual work, either that is done by the system or that system needs, and the work for the reversible very ideal case. Now, let's talk about turbines. Again, the objective of turbines is to generate a power. Okay, so generate work. Now, before we talk a little more about the turbine, we always assume that this turbine is adiabatic, meaning that we don't allow any auxiliary heat loss from the turbine to the surroundings, diabatic. Okay. Now, let's assume two turbines. One is actual turbine, okay, as you see here, and the other one is ideal turbine, which means a reversible turbine. Now, let's assume that we have the same inlet condition, which is P1 and T1 for both turbines. And now, we design these turbines to have the same exit condition in terms of pressure, P2. Okay, but depending on the processes inside the turbine, the temperature will be different. And as a result, the enthalpy at the exit also should be different. Now, let's think about the ideal case. Okay, and yeah, so let me try to write up the second law of thermodynamics to make you a better understanding of what's going on inside. All right. Now everything is based on the steady flow conditions. So now if you try, and it's an open system. So if you try to write the first law of second law of thermodynamics for an open system, and there's flow the steady flow condition, the left hand side starts with 0. So then basically that is the change of entropy of the control volume, which should be equal to 0. And this is due to the entropy transfer. Now we also have entropy flow from inlet and outlet and entropy generation rate. Now we already assume that we have 0 heat transfer. Okay. Based on this equation, let's think about the ideal case where the reversible process happens inside a turbine. Well, in that case, the reversible means you have 0 entropy generation rate. Okay. So now, if you look at the second law of thermodynamics equation, we don't have entropy generation. So from this equation, we can see that when your turbine is ideal, like a reversible process, then you must have entropy at the exit equals to entropy at the inlet. Okay, so that is very important condition that you have to remember for ideal case. Now, what if your turbine is actual or irreversible? Irreversible means that you always should have a certain entropy generation. So now in the case, your entropy generation rate should be always positive. Now, then by looking at the second law of thermodynamics equation that I wrote down here, Sg is positive. So what you can see is always the entropy at the exit S2 should be bigger than entropy at the inlet. Okay. Now let's move to the diagram. So in the case, I just I'm showing the HS diagram, but in fact how it looks in HS diagram is pretty similar to TS diagram. Okay, so I'm gonna just use it both, but at this moment, so let's try to see the H and S diagram, where we can draw this constant pressure curve as this basically now for constant pressure P1 and constant pressure P2, that is exit condition. And the point 1 is basically your inlet condition. Okay. Then if you really think about the ideal turbine, then your ideal turbine makes the entropy the same between the inlet and outlet. So its HS diagram gives us vertical line because it does have the same entropy, right? And in order to distinguish this ideal case with from actual case, let's use a subscript 2s. So from now on, when you see s at the end, that means more likely ideal or isentropic process. Okay. Compared to the ideal case, the actual case always gives us bigger entropy at the exit. So we have 2a. And now we have the expansion process from 1 to A. And please remember that how we draw the solid line and dashed line. So dashed line actually means that it's not so something we don't exactly know. Okay, so that is a really totally irreversible process. So that's why we just try to draw dashed line. Many times we don't care, but just I want to emphasize that if you see that dashed line there, then it means that we don't know exactly how that expands. Okay. Right. Then from lecture note 14, the turbine work can be written as turbine work per unit mass can be written as inlet enthalpy minus inlet at the exit. Okay. So with that being said, the ideal turbine work can be written as H1 minus H2A, and actual turbine work can be written as H1 minus H2S. Oh, sorry. So in the case is 2S, and that is 2A. Okay. So always the difference of enthalpy values between the inlet and outlet gives you the turbine work per unit mass. And from the HS diagram, right, the ideal case, ideal turbine has a lower or smaller enthalpy at the inlet than the enthalpy at the actual turbine outlet. Okay? So as a result, we always have a larger turbine work for the ideal case than the actual case. So we can define the turbine efficiency or the isentropic efficiency of the turbine as a ratio of actual turbine work which is smaller than the isentropic turbine work, right? To the isentropic turbine work, which is W, let me just rewrite it, WTA divided by WTS. Okay. And because always WTS, which is ideal case, is greater than WTA, well, the isentropic efficiency of a turbine is always smaller than 1. Yeah. Or we can express the turbine efficiency as the enthalpy difference between two turbines, like actual and ideal. Then how about the compressors and pumps? Same thing, we assume that they are adiabatic. Then same thing happens. Okay? Obviously, to run the compressor and pump, we need certain work in to those devices. And as a result of running this compressor and pump, we have higher pressure, okay, and or high enthalpy. So that is how we see the HS diagram here. Okay. Now, by following the exactly same kind of discussions as we did for turbine, we can easily understand that the ideal case, the reversible turbine, reversible compressor, gives us the same entropy, between the inlet and outlet. Okay, so in HS diagram, we have vertical line. For actual compressor or actual pump, we have greater entropy at the exit than the inlet. Okay? And as a result, we have this kind of curve. And from lecture note 14, we can calculate the compressor work as exit enthalpy minus inlet enthalpy. So from this equation, we can write it out, the ideal compressor work as H2S minus H1, and same thing, HCA, actual compressor work as H2A minus H1. And by comparing those values of H2S and H2A and H1 in HS diagram, we can see that always, okay, the actual compressor work that we need should be bigger than the ideal compressor work. So then we can define the compressor efficiency or the isentropic efficiency of the compressor as a reverse of that of turbine. In the case, the compressor efficiency is defined as the isentropic or ideal compressor work in the numerator divided by actual compressor work in the denominator, or WCS divided by WCA. Okay? And by using the first law of thermodynamics equation, then we can write the compressor efficiency as this equation. The same definition can be used for pump because intrinsically the compressor and pumps are basically the same. Only the difference is that for the pump we use incompressible working fluid. Okay, but the definition of the pump efficiency is the same as the compressor, meaning that we compare the isentropic pump work to the actual pump work. Okay? But in terms of calculating the ideal pump work, in other words, reversible work, okay, for an incompressible fluid, please you look at lecture note 20, where you can find out Ws can be written as V, the specific volume, which doesn't change, times P2 minus P1. Here P2 is the exit pressure and P1 is inlet pressure. Okay, so by using this equation, then we can write up the pump efficiency as it looks here. Okay, then how about the isentropic efficiency of nozzle? So all objective of using nozzle is to increase the velocity at the exit. Okay. Now, if you look at the lecture note 14, what we can see and what we at the time derived in terms of the first law of thermodynamics was H1 plus V1 square over 2 is equal to H2 times V2 square over 2. Many times because at the exit nozzle velocity is much higher than the velocity at the inlet of nozzle, we ignore this portion. Okay. So from this equation, what you can see is that the difference of enthalpies at the inlet and exit gives us the increase of your velocity at the exit. Okay. Or your inlet enthalpy gives you a certain the value of enthalpy at the exit and your velocity increase at the exit. So that is how we understand it. Okay. Now, how can you draw the HS diagram based on the understanding of what happens inside the nozzle? So in that case, now we can still look at the same thing. Now we have the constant pressure curve and constant pressure curve for the exit. Now, when you think about what should happen in terms of a second law of thermodynamics, same thing. When you kind of thought about the turbine, okay. So now by looking at the second law of thermodynamics, still we assume that your nozzle is adiabatic. Such that we don't have to worry about the entropy transfer. And okay, so for the ideal case, ideal nozzle, we still don't have any entropy generation, so it's gone. So even for the nozzle, if the nozzle is very ideal, very reversible, then your entropy shouldn't change. So in that case, ideal nozzle has a vertical line from 1 to 2s. For the actual nozzle, we have positive entropy generation. So as a result, the entropy at the exit of the nozzle should be greater than the entropy at the inlet. So we also have that kind of pretty similar curve as we saw in the nozzle, in the turbine. Okay, but the difference between the inlet enthalpy and outlet enthalpy gives us the increase or the velocity at the exit, or in terms of kinetic energy. Okay. Then we can define the nozzle efficiency as the actual kinetic energy at the nozzle exit, which is smaller than the ideal kinetic energy we gain at the nozzle exit. So we compare the actual kinetic energy to the ideal kinetic energy. Okay. Then we can write up this way, right? So because kinetic energy is simply 1 over 2, V square. Then, because we know from the first law of thermodynamics that H1 equals to H2 plus V square over 2, then by combining this first law of thermodynamics, so let me just write it down. So that's the first law. And the definition of the nozzle efficiency, we get the same enthalpy changes between the inlet and outlet, even for nozzle. So basically this equation itself looks exactly the same as the turbine efficiency.